Hey everyone, Mr. Cummings here, and welcome to this video on impulse and force versus time graphs. So we'll start this video by taking a look at a constant force over time graph. So we're going to assume that we have a constant force F naught applied to a cart over a duration of time delta t. So we would get a graph that's just a flat graph over time, and if we shaded in this region, we'd see that we have the area of a rectangle here. So the area of a rectangle is going to just be base times height. So we'll have our base of delta t and our height of F naught, and it doesn't matter which way we organize those since it is a product. So we can say that the area is F naught multiplied by delta t. And so from our previous learning, we know that if we have a force multiplied by a time duration, that's actually equal to the change in momentum of an object. So to answer our second question, what does this area represent? The area under a force versus time graph represents the impulse delivered to the object or the change in momentum of that object. So once again, to formalize this note here, the area under a force versus time graph represents the impulse or the change in momentum of an object. And if we use the area alongside something like the momentum equation or the change in momentum equation, it can allow us to solve for things like the initial velocity of an object, the final velocity of an object. We could solve for the mass of an object, so on and so forth. So whenever we're given a force versus time graph, thinking about equating the area of that graph to the change in momentum is going to be a pretty powerful tool and a good way to solve a lot of problems. So most graphs for force versus time and collisions won't be a flat line. Instead, they're going to resemble some kind of a force spike, meaning that the force increases as the collision starts, and it decreases back to zero as the collision ends, as the two objects separate. So if we wanted to look at calculating the area of something like this, we would just recognize that this is a triangle, and we can do area of a triangle as 1/2 base height. The base is going to be delta t, and the height here is going to be the maximum force that is exerted on the object during the collision. So writing this out, if we wanted to analyze the area of this graph, we would say that the area is 1/2 F max multiplied by delta t. And once again, that is equal to the change in momentum delivered by that force, or the impulse delivered by that force. So if we were to take that idea of a force spike graph being created whenever you have a collision, and then we look at a collision between two objects, and we look at the force time graph of both objects at the same time, we'll see some pretty interesting patterns develop. So say we have object A moving to the right and object B moving to the left, and they collide. If we graphed the force versus time on object B from object A, we would get this blue graph here. So we see that we have positive x is the right direction, so object B is moving negatively, but when A collides with it, it exerts a force on B to the right. Now as it starts making contact, that force will increase in magnitude, reaching some maximum during the highest point of the collision, and then as they lose contact, as they bounce off of each other, that force will decrease in magnitude. And the area under here would be JB, which would be the impulse on object B. Now if we look at the same thing for object A, we know that the forces exerted from object A onto B and B onto A are a force pair. So they are going to be equal in magnitude at all times and opposite in direction at all times. So we're going to get the mirror image of the force of A on B as the force of B on A. So we're going to get a negative force spike graph where the area here is going to be a negative area, and that's going to be the impulse delivered to object A. So here we can see that the total impulse on each object or in the whole system is going to be zero, because you're going to get a positive impulse on object B and then a negative impulse on object A. And that leads to a pretty powerful statement. We're saying here that the total momentum change of the whole system is actually going to equal zero because of Newton's third law. And so once again, just to kind of reiterate what we went over in this video, the areas of these force time graphs are impulses. When we have a collision between two objects, we do have Newton's third law, which tells us that the impulses are going to be equal and opposite, meaning the momentum of each object is going to change by the same magnitude, but in opposite directions. And that's going to be it on this video going over impulse and force versus time graphs. Thanks for tuning in, and I'll see you next time.